Welcome back to the Deep Dive. Today we are witnessing, well, a genuine moment of reckoning in the pursuit of artificial general intelligence. We are diving into the launch of ARC-AGI-2, the next generation benchmark that promises to be the toughest test yet for our most advanced AI systems.
And this deep dive is crucial for you because we aren't just looking at a new test. We are confirming the obsolescence, really, of the old one. Our mission today is to understand why the original ARC benchmark, ARC-AGI-1, which, defined the field for years, was ultimately insufficient. And also how researchers specifically engineered this new challenge to resist the current strengths of AI, and what the initial, frankly, kind of shocking frontier model scores tell us about how far we still have to go.
Right. Let's maybe start with the foundation. For those who might be less familiar, ARC-AGI-1, launched back in 2019, was pretty groundbreaking at the time. It assessed general fluid intelligence using these simple input-output grids of colored cells. The whole idea was minimal prior knowledge.
Exactly, just basic cognitive stuff like symmetry, object persistence, counting, that sort of thing.
Yeah, and crucially, no specialized world knowledge, no language processing needed. It was meant to be easy for humans, baffling for machines. Okay, let's unpack this. When ARC-AGI-1 launched, I think everyone expected AI scores to climb steadily.
Yeah.
Yet for years, despite just massive scaling of large language models, I mean, we're talking base LLM scaled up by a factor of 10,000 times between 2020 and early 2024.
Right.
The state-of-the-art scores just stalled hard, around 34%. On the hidden private evaluation set.
And here's where it gets really interesting. That plateau, it was suddenly and, violently broken in 2024. A lot of that was spurred by the ARC prize competition. The winning eligible score jumped all the way to 53.5%.
Wow, quite a leap. What caused that?
That leap was driven by a key set of innovations called test time adaptation, or TTA.
Okay, TTA. That sounds like serious technical jargon. Can you maybe break that down for us a bit?
Sure. Think of TTA as well as throwing huge amounts of computing power at the problem during the test itself. It's essentially letting the AI rapidly guess and check, millions of possibilities until it stumbles upon a sequence of actions that gives the right answer.
So less about finding the underlying logic efficiently.
Precisely. It uses massive search algorithms or iterative gradient descent applied dynamically right at the moment of the test to synthesize potential solutions. It's a powerful engineering trick, definitely, but maybe not a great signal of generalized intelligence.
And that technique, that TTA, led pretty quickly to the saturation point, right?
Yeah.
Late in 2024, we saw previews of OpenAI's O3 model. Using TTA, it hit 76% on the semi-private evaluation set with a relatively low compute setting.
Right, estimated around $200 per task, which is still quite a bit.
True, but then the high compute setting achieved an astonishing 88%.
Yeah, but let's not lose the forest for the trees here. What did these massive costs fundamentally reveal? I mean, while 88% technically surpassed the nominal human baseline, that high-end score required an estimated $20,000 of compute per single task.
$20,000 for one puzzle.
Exactly. This confirmed the worst fears. The benchmark was approaching saturation not through efficient generalizable reasoning, but through sheer brute force and, an absolutely astronomical computational budget.
That's a crucial distinction, isn't it? We proved we could pay our way to a high score, not necessarily think our way there. That $20,000 price tag for one abstract puzzle really suggests the performance was more a testament to economic power than, say, cognitive progress.
Absolutely. That massive cost was really a symptom of two major structural flaws in ARC-AGI-1, flaws that compromised its signal for genuine AGI progress.
Okay, so if nearly half the tasks could eventually be cracked by, throwing $20,000 in compute at them, does that suggest the original problems are just too simple, or was it more that the models learned how to game the system?
Well, it was kind of a bit of both, actually. And that leads us straight into the first flaw: susceptibility to brute force. A meta-analysis from the 2020 competition found that 49%, almost half of the private evaluation tasks, were eventually solved by these computationally intensive, exhaustive search methods.
So basically, for half the test, abstract reasoning was kind of irrelevant. You just needed enough time and money to try everything.
Pretty much. It diluted the signal we were looking for. And the second flaw had to do with data management, as you hinted.
Right, the information leakage.
Precisely.
Right.
The second major limitation was the risk of information leakage. The issue is consistency, maybe too much consistency. The same 100 private evaluation tasks were reused across 4 major competitions from 2020 to 2024.
4 years using the same hidden set.
Yep. And over those 4 years, thousands of scores related to that hidden set were disclosed publicly. This created a huge risk that research teams were implicitly tuning their models to the specific quirks, the idiosyncrasies of those exact 100 tasks, rather than advancing riffing that works on any novel task. Ah, okay. So overfitting to the test itself. Plus, I remember the original human comparison wasn't super robust either.
No, it wasn't. The initial assessment was based on only 2 human testers who scored very high, 97% and 98%. So we confirmed ARC-AGI-1 saturated below true human fluid intelligence levels, and we just lacked solid first-party human testing data collected under consistent conditions for a proper comparison. Okay, so the designers of ARC-AGI-2 had a really clear mandate. They needed to keep the core principles, easy for humans, hard for AI, no prior world knowledge.
Keep the essence.
Right. But engineer the tasks to actively minimize susceptibility to those, well, let's call them lazy, computationally intensive, brute force search techniques. They had to force efficient conceptual adaptation.
And based on the human testing reports, the difficulty has definitely been ramped up. These new tasks require much more deliberate thinking. The average time for a human to complete one successfully was, 2.7 minutes?
That's right. Compare that to many ARC-ADI-1 tasks that, human testers could often solve almost instantaneously. Big difference. So this raises an important question. What exactly makes these new tasks so much harder?
The key design principle is forcing deeper levels of compositional generalization. That's a bit of a mouthful, but
Break it down.
basically, it's the ability to flexibly combine known rules or concepts in brand new, complex ways, like building a unique little mental program for every single new task you encounter.
Okay, let's look at some examples of how they specifically tried to defeat that brute force approach. They introduced multi-rule compositional reasoning. What does that actually look like in practice?
So instead of just one high-level transformation, like, say, all red objects move left, these new tasks might demand 3 simultaneous operations. For instance, a task might require you to first crop the input grid, then rescale every object you just cropped, and finally place those rescaled objects into corresponding holes, all at once, conceptually.
Wow, okay. That sounds like it breaks those simple search strategies.
It does. Current AI systems really struggle with that kind of simultaneous, integrated execution. And then they also tackled sequential complexity with multi-step compositional reasoning.
Right, so this is about steps depending on previous steps.
Exactly. Here, the process is sequential, and crucially, the outcome of step N depends directly on the precise state resulting from step N1. This is critical because it means you simply cannot predict the final end state without executing the previous steps one by one.
So brute force methods that try to just guess the final answer are useless here.
They fail immediately, yeah, because the intermediate states are unpredictable without actually doing the work. It demands genuine planning and execution simulation.
Okay, the next one sounds really interesting. Contextual rule application. How does context change the rules?
It means the core transformation rule itself is conditional on something else in the input. So you might have a basic rule like stack the shapes, but the direction you stack them, maybe left or right, is determined by a contextual element like the color of the shape's outline.
Ah, so the AI has to look beyond the immediate action.
Yes. It has to derive a condition from the context and then compose the main transformation rule with that conditional rule. It really forces conditional reasoning.
And the final piece seems designed specifically to trip up models trained on vast data sets. In-context symbol definition.
Oh, this one is truly a major hurdle for current frontier AI systems. The tasks feature symbols like, say, colored rectangles with different numbers of holes, whose meaning is defined only within that specific task.
So the symbol doesn't mean anything universally.
Nope. For example, a blue rectangle with 2 holes might mean, for this task only, use the color red for every object that has an odd number of sides. The AI can't rely on rules or concepts it learned from scraping the web yesterday. It has to invent a new conceptual language right now, just for this task.
Yeah, kind of flexibility.
Yeah.
Yeah, I can see why current large models would struggle with that.
It's precisely what they lack.
Now, a huge improvement over AGI-1 was how they established the human baseline this time. Much more rigorous. They ran extensive, first-party human testing under controlled, standardized conditions, things like 90-minute sessions, base pay, plus a $5 incentive for every correct task.
And what's really fascinating here is what those human results revealed about the nature of the test itself. It wasn't just about setting a score. They confirmed that ARC-AGI-2 seems to be truly assessing general cognitive ability. The study found no statistically significant correlation between how well people performed and various demographic factors.
Wait, really? No correlation with occupation, technical experience, programming skills, even math background?
None that were statistically significant. Whether you were a programmer, a historian, a mathematician,
Yeah.
it didn't predict your score on these abstract puzzles.
That's actually amazing. It suggests the tasks genuinely tap into pure domain-independent fluid intelligence, doesn't it?
Exactly. It implies the human mind is employing some kind of generalized problem-solving architecture that is independent of specialized expertise, which is, precisely the goal of AGI research, finding that general capability.
Let's put some numbers on that human performance. They had, what, 407 unique participants?
Correct. 407 participants, and they logged over 13,000 attempts in total. And remember that average completion time we mentioned? The median time spent on tasks they successfully completed was just 2.2 minutes.
Only 2.2 minutes on average for these complex tasks.
Yep. And this really sets the new bar. 75% of people who attempted the final ARC-AGI-2 test pairs managed to solve them. And crucially, 100% of the tasks were solved by at least 2 different people in 2 attempts or less. So the benchmark is hard, definitely, but it's clearly accessible to human reasoners.
Okay, now we get to the sobering part, where we check how the current state-of-the-art AI models actually stack up against this new, much higher standard. And the results are pretty stark, aren't they? They seem to prove the benchmark really succeeded in moving the goalposts entirely.
Yeah, stark is the right word. We can look directly at the initial performance data, the models that were actually competitive on the old test. They're barely registering above noise level on ARC-AGI-2. Take the architects, for example. They were the 2024 prize-winning team on AGI-1. Their score dropped from 56.0% accuracy on ARC-AGI-1 down to a mere 2.5% on ARC-AGI-2.
Wow. Okay, from 56% to 2.5%. That's an insane drop. Are researchers sure that 2.5% isn't just random chance? Is it truly just noise?
That 2.5% and similar scores are generally considered to be noise-level heuristics, yes. It basically confirms that the methods that brought them success before, primarily that test-time adaptation and massive computational scaling, are simply failing. They're not finding consistent generalizable logic on these new, harder tasks.
Any other model examples?
Sure. The O3 medium model from OpenAI, which got 53.0% on AGI-1, also plummeted, down to 3.0% on AGI-2. The key takeaway here is pretty clear. The brute force search strategy, just throwing compute at it, it seems dead for this class of problem.
So the challenge is now officially laid out. There's the ARC Prize 2025 competition, right? With a big prize pool.
A very big one. A total prize pool of 1,000,000 USD.
And the grand prize.
The massive target for the grand prize is $700,000. It goes to the first team, or teams, to achieve 85% or higher accuracy on the hidden private evaluation set of ARC-AGI-2. But crucially, the evaluation protocol emphasizes the efficiency the old tests lacked.
No, so?
The system has to solve 240 unseen tasks within a highly restrictive 12-hour wall clock window. And here's the kicker. Using only 4 NVIDIA L4 GPUs.
Only 4 L4s. That's modest compared to the compute used before.
Exactly. That hardware limitation means success is entirely dependent on achieving true, efficient generalization. You can't just throw compute at the wall anymore. You have to actually reason effectively. Hashtag tag outro.
So what does this all really mean? It feels like ARC-AGI-2 has effectively hit the reset button on scoring AGI progress, at least in this domain. It's a clear signal, isn't it? Simply scaling up current deep learning models or just relying on that computational brute force.
Yeah.
It's not enough anymore to solve these abstract reasoning challenges.
That's right. The focus for research really has to shift now, squarely onto efficient, flexible, and truly generalizable compositional reasoning, the very thing that current frontier models just spectacularly failed at on this new test.
A whole new direction, potentially.
And this is where we'd like to leave you, the listener, with a final provocative thought. Think about the human participants. They solved these incredibly complex problems in a median time of just 2.2 minutes. And we saw their success was independent of their professional background. Now, if the current best AI score is struggling down there at 3%, what cognitive mechanism are humans actually utilizing in those 2 minutes? What allows them to invent and execute new conceptual rules on the fly, solving problems that billion-dollar AI systems cannot yet even touch? That mystery. That's the new frontier.